In this video, we'll discuss how radiation therapy can be framed as an optimization problem. The data is collected in the treatment planning process, which starts from a CT scan like the one you see here on the right. Using the CT scan, a radiation oncologist contours or draws outlines around the tumor and various critical structures. In this image, the oncologist would contour structures like the parotid or saliva glands and the brain. Then, each structure would be discretized into voxels or volume elements, which are typically 4 millimeters in dimension. The second image here shows a close-up image of the brain, and you could see the small squares which represent the voxels. Here they're two-dimensional, but in reality they would be three-dimensional. Now we can compute how much dose each beamlet or piece of the beam delivers to each voxel. We'll start with a small example. Suppose we have 9 voxels and 6 beamlets. Our voxels can be categorized into 3 types: the tumor voxels, which are colored pink, the spinal cord voxels, which are colored dark green, and other healthy tissue voxels, which are colored light green. So we have 4 tumor voxels, 1 spinal cord voxel, and 4 other healthy tissue voxels. We have 2 beams that are each split into 3 beamlets. Beam 1 is composed of beamlets 1, 2, and 3, and it comes in from the right. Beam 2 is composed of beamlets 4, 5, and 6, and comes in from the top. Our objective is to minimize the total dose to healthy tissue, both to the spinal cord and to the other healthy tissue. We have 2 types of constraints. The first is that the dose to the tumor voxels must be at least 7 gray, where gray is the unit of measure for radiation. Our second constraint is that the dose to the spinal cord voxel can't be more than 15 gray, since we want to be really careful to protect the spinal cord. We know the dose that each beamlet gives to each voxel at unit intensity. This table shows the dose that each beamlet in beam 1 gives to the voxels. Remember that this is at unit intensity. If we double the intensity of the beam, we double the doses. The dose to each voxel can depend on how far the beamlet has to travel or the type of tissue that the beamlet has to travel through. Similarly, we know the dose that each beamlet in beam 2 gives to each voxel, again at unit intensity. The dose again depends on the direction of the beam and what it travels through. Putting these tables together, we can now write out our optimization problem. Our decisions are the intensities of each beamlet. We'll denote these by x1, the intensity of beamlet 1, x2, the intensity of beamlet 2, x3, the intensity of beamlet 3, etc., for all 6 of the beamlets. As we mentioned before, our objective is to minimize the dose to healthy tissue. So we want to minimize the total dose beamlet 1 gives to healthy tissue, which would be 2 for this first voxel, plus 1 for this voxel, times the intensity of beamlet 1, plus 2 plus 1 times the intensity of beamlet 2 for the spinal cord and the other healthy tissue voxel. We can continue in this way, adding up the total dose that each of the beamlets will give to healthy tissue. And finally, beamlet 6, 1 plus 1 times x6. Now our constraints. First, we want to make sure that each voxel of the tumor, or the pink voxels here, gets a dose of at least 7. Let's start with the first tumor voxel in the top row. This one's going to get a dose of 2 times the intensity of beamlet 1 plus 1 times the intensity of beamlet 5. This needs to be greater than or equal to 7. Similarly, for the second tumor voxel, we want 2.5 times the intensity of beamlet 2 plus 2 times the intensity of beamlet 6 greater than or equal to 7. And now we'll just repeat this for the two tumor voxels in the last row. 1.5 times x3 plus 1 times x4 greater than or equal to 7, and 1.5 x3 plus 1 x5 greater than or equal to 7. Lastly, we need to add our constraint for the spinal cord. The total dose to the spinal cord, which is 2 times x2 plus 2 times x5, needs to be less than or equal to 15. We also want all of our variables to be non-negative, so x1, x2, x3, x4, x5, and x6 should all be greater than or equal to 0. Now that we've set up our optimization problem, we'll solve it in LibreOffice in the next video.